kind of issue. That way I don't forget. I posted the Unit 4 Lesson 2 notes and lesson this morning for anybody who needs to catch up or rewatch. So we're going to go ahead and get started. Today we're doing Unit 4, Lesson 3. Our topic is mixtures and solubilities. And so once again, this unit, this and the next class's lesson is the last part in mixtures. And then after that, when we come back from winter break, we're starting the introduction to chemical reaction at that point. And so go ahead, write the lesson title down. We're going to go ahead and get started. I believe I had told you all this last class period that everything we had done up until this point technically was not a mixture. Everything we were studying had been pure substances. So now we are finally going to look at what happens when we mix pure substances together. Mixtures and solubility. The reason why this is important is when we get into chemical reactions, most of the reactions that we're going to do take place in a solution of water. And so when we are mixing chemicals, most things are something that's dissolved in water. So we need to discuss what dissolves in water, how much dissolves in water, and we're going to do that today. So here we go, mixtures and solubility. Once again, some of this may be review and some of it will be new. Just like the state of matter lesson, some of that was review and some of that is new, like from other science classes. All right, so you're going to see here, I printed this chart for you.
Thank you, teachers. Juniors have been released. They are on their way back to class. They should be back to class within the next 2 minutes. Thank you very much.
You want to write on your handout, this is kind of the top of the diagram a little bit. This top is matter. And in the beginning of this year, we defined what matter was. Does anybody remember? It's been a while. Actually been here for what, 4 months now? 4 months. Yeah, it's been 4 months. Doesn't seem like that. Well, 4 months ago, almost, or probably 3.5 months ago, we defined matter in Unit 1 when we were first learning an intro to the subject. And so, what's matter?
Everything of anything.
Anything that has mass and occupies an amount of space, which is volume, right? Anything that has mass and occupies space, which we also know as volume, right? And so we classify atoms as the simplest building block of matter. You're done? Because atoms have, albeit a very small mass, they do have mass. And as we know from the cloud models, they do occupy a certain amount of volume. We know that there is an atomic radius. And so as small as an atom and to everything that we see, we classify all of that as matter. And so what we're going to look at now is a summary of types of matter. And so what we have studied up until this point has been substances. And when you have a substance, the composition is always the same throughout the entire substance. And there are 2 types of substances you need to be aware of. We've learned them both. Elements, this is single, capital letters on the periodic table. So found on the periodic table if you want to write that. And compounds, which we know are 2 or more elements that are combined in a fixed ratio. That are stuck together. Either they're stuck together through an ionic bond where they're transferred electrons, or they are stuck together by a covalent bond where they had to share electrons in order to form the compound. And we spent all of Unit 3 talking about that. And so really, we don't give nearly as much love to mixtures. We're going to talk about them here, and then they'll be sprinkled throughout the class because all the work we do will be in solution, which is a mixture. And so the 2 types of mixtures you need to be aware of, which you might have heard in middle school or you might not have, are homogeneous and heterogeneous mixtures. And so you'll want to circle and you can't really tell the difference in what you see. So, for example, I got out some tap water. Tap water is a mixture. What's in tap water?
Oh, there's like.
You know, there's water
other
in tap
things that
water,
they add.
but what else is added into the water supply? Fluorine, F minus
It's
specifically.
not like distilled water, that's why.
It's not distilled water. There's other things in there. Potassium
Yeah.
Isn't there? Because of those ions.
Yeah.
And so we would actually classify tap water as a mixture, not as a, well, it's got minerals in it
Yeah.
because all those elements, those ions, are actually what we call minerals.
Yeah.
It's got magnesium in it. It's got a bunch of different things that are allowed to be drank for the most part.
Hopefully.
Hopefully, our water is safe.
We don't need an incident where you light your water on fire.
And so the difference between a homogeneous mixture and a heterogeneous mixture is in a heterogeneous mixture, what you have exists in multiple phases, and you can separate the mixture quite easily. And so, not mix thoroughly is a quick way to define a heterogeneous mixture. For example, if I go and I get a milkshake with whipped cream on top, the whipped cream is not mixed in, it's a layer on the top. And so we would call that, tasty, maybe, and we would call that a heterogeneous mixture. Likewise, if I take water and I put oil on the water, that's going to be a heterogeneous mixture because I can separate the oil from the water. They don't mix together. If I try to mix them together, they'll re-separate into two distinct.
It's heterogeneous if you can separate it.
Separate it
And
physically.
it's homo when you can't separate it.
When you can't separate it as easily.
Okay.
And so we're going to go into the specific definition shortly, but this is just a flow chart on substances and mixtures. And so these are the definitions you need to be aware of for mixtures. A mixture itself is a physical blend. Physical means that it can be separated by physical means, either pouring off a layer in the top, by filtering, like using filter paper. And so a mixture is just two or more compounds together. So when we say two or more components, these components could be different pure substances. Meaning some kind of combination of elements, ions, compounds. Talking back about tap water, what would be the way to separate ions out of tap water? What do people do? You boil it. That's a fancy name called distillation, actually, is the actual process, which is why it's called distilled water. Because you boil out the water and all the salts are left at the bottom of the mixture at the end. You collect the boiled water into a different container and then recool it down, and then that's your distilled water. That's just pure water. But we call that a physical process because we're just boiling. That's why it's called a physical process to separate. So you can separate both homogeneous and heterogeneous mixtures through physical processes. And so the two types of mixtures you need to be aware of are heterogeneous, where the composition is not the same throughout. I would also say, you could say it's two or more phases, is another way to understand it. Whereas a homogeneous mixture is one phase. Everything looks the same in a homogeneous mixture. And so the examples you'll see for heterogeneous mixture, the one example on the left is trail mix. In trail mix, you've got your M&Ms, or chocolate candy. You've got raisins. You've got almonds. You've got peanuts. And you can pick out all the different pieces from each other. So with a heterogeneous mixture, you can always easily separate the components because you can visibly see the different components. Whereas in a homogeneous mixture, because you can't see the components in the mixture, they're mixed very thoroughly. You have to be more creative in terms of how you do that separation, which is why I mentioned distillation, like boiling or filtration. There's a couple other methods. Another one's called chromatography, if you did that in biology. Most of the year will be focused on homogeneous mixture, which you can also call homogeneous. It's like potato. You could say it either way, homogeneous or homogeneous. And depending on what resource or who you're talking to, they'll use one of those two. We're going to study homogeneous mixtures way more than we're going to study heterogeneous mixtures in this class, because we're going to study predominantly solutions where water is involved, and water, you're going to go over shortly, is the universal solvent, meaning it dissolves a lot of materials. And so most of what we're going to work with is homogeneous mixtures, which we also call solutions of solutions. All right, so I'm giving you some time, and then we'll continue. What we have to address after defining whether something's heterogeneous or homogeneous is we have to define what dissolves in water and what doesn't. And then the second question is how much dissolves in water, what is the limit? And we call that solubility. Just giving you about a 20-second heads up that I'm moving forward. Okay, moving forward now. So the first type of question you can be asked here is, would each of the following be best classified as a pure substance or best as a mixture, and then as which type? You can use your flow chart to help you. However, you do need to memorize what are your types of substances. Is it a pure substance or a mixture? And then what are the individual types? Air is not a pure substance. Right. Right. I'm giving you some time to write it down, and then we'll go over each one together. Remember, in the flow chart, it was classified what is a pure substance and what is a mixture. You may want to look back over that again before you make the decision. Yes. Go ahead. Ammonium nitrate. Pure substance or mixture? Pure substance. Ammonium is NH4+. Nitrate is NO3-. Together that makes the compound NH4 NO3. This is a compound we learned how to name, and compounds are classified as pure substances because they are the same throughout. It's the exact same elements fused to each other, ammonium nitrate cannot be physically separated. It can only be separated via chemical reaction. So if you have been given something that you have learned how to name in this class, you've been given a compound. If I tell you carbon dioxide, that's a compound. If I say sodium chloride, that's a compound. Ammonium nitrate, also a compound. So it's a pure substance. We've studied it before. And it's specifically, gotcha on the first one. But no, you know. All right, air, some of you already started to work out. I had also, I believe, mentioned it as an example last class of a mixture. Air has a bunch of gases. They are not fused together, yes.
Take pictures of anything going on.
Well, yeah, there's a lesson.
Is it okay?
Come on, anybody who has an ugly sweater.
Oh no, it's not for ugly sweaters.
Oh,
It's for the class.
Like,
Oh,
no, there's nothing interesting going on. Come back to these.
Oh, they're too purple. That's the thing.
There's nothing going on. So, I can send you pictures. Okay, just remind me.
Okay.
I'll email you. They're doing a lesson. Yeah. I will send you pictures. Because the lab we're doing on Wednesday is cool, so that would be the time to take pictures. I don't want to spoil it, but when I said pre-1982, you could look it up.
Are you gonna be removing the?
You'll see.
menu?
That's part of what you have to do, but that's not really cool.
You get the.
Were that in the 40s since they had to use copper for
I
World War
was gonna
II?
bring my pen.
The pennies were
Those are
pretty
good.
made.
So not wheat pennies, somewhere between 1950 maybe and 19, not wheat pennies.
Wheat pennies are like what the fuck?
That's why I said don't bring your wheat pennies if you have those. Just bring anything that's after the wheat pennies, but before 1982 would be the best. They're not really worth anything.
And after the war too.
Yeah.
Those are-
So after 45.
I have a penny for.
45 to 82. That's the sweet spot. That's the pennies we're looking for the lab. Not worth anything, but cool reaction. So,
I have it all filled.
all right, air. Let's go back. Air is a mixture of a bunch of different gases. It's got like some nitrogen in it. It's got some oxygen in it. It's got some hydrogen in it. A little bit, not too much, or else the air would explode. When fire. It's got some carbon dioxide in it. It's got some. I'll say helium in it. Yeah, I said CO2. And et cetera, et cetera, et cetera. Trace amounts of other noble gases like neon. So there's a decent amount of components. Hopefully you don't also have that much carbon monoxide in your air.
You're a doctor.
And so air is a mixture of a bunch of gases. They're not fused together. So therefore, we would say it's a mixture. Now, can you see different phases and separate them in air?
In the air,
You
right?
can. I can't.
Oh,
We would classify it. That's funny. It's a homogeneous mixture. That's what most people, unless you have superpowers, it's a homogeneous mixture. Homogeneous. It is not an element. Air, I cannot find it on the periodic table. And it is not a compound. It is a mixture of elements and compounds that we cannot easily separate. They exist as one phase. Salt water. Mixture. NaCl plus H2O. It's got at least two components. It's a mixture. And
Salt and water.
it's going to be homogeneous because salt is salt. Specifically. Whereas if I said oil and water, it would be a mixture, but it would be heterogeneous. And then we're going to learn very shortly what mixes in water and what doesn't. Caesar salad. Sure.
Nah,
Which
of course
compound
it's
is it?
pretty soft.
You got the lettuce and the lettuce. And the
Lettuce is a compound.
It's the C from the
Mixture.
Caesar is from the carbon off.
Caesar salad. At our simplest, like easiest understanding of what a basic Caesar salad is, it's going to have Caesar dressing, it's going to have lettuce, and it's going to have, I would say, croutons, heterogeneous.
I've Caesar salad.
I've never had a Caesar salad.
I mean, at the most basic, lettuce, Caesar dressing, bam, Caesar salad. You can still mix.
I didn't know there was like, no, I know there's Caesar salad. You know,
It's a
Caesar,
mixture of
like,
heterogeneous
dressing.
type. Aluminium,
Pure substance.
substance. Of which type?
You find old Al in the periodic table.
You can find it on the periodic table. We classify it as an element. Yes, this is the type of question you can be asked on the Unit 4 test. Elements, find them on the periodic table. Compounds, also find them potentially on the periodic table. Anything that we've named, right? Any fusion of elements that are ionic or covalent compounds. And then mixtures, most of it is what people would say is common sense to be able to figure out mixtures. So you can be tested on anything that exists and asks what type of mixture it is, homogeneous or heterogeneous. All right, we're gonna go ahead and continue. So I said that we were gonna look at both heterogeneous and homogeneous mixtures, but we're gonna spend the most time in homogeneous mixtures because most of, or I'd say almost every chemical reaction we do, almost everyone, is going to involve water in some way. And something that's dissolved in water. Because water allows ions to move around, and so because they're able to move around, the chemical reaction happens a lot easier than something that's in the solid phase. And so let's go ahead and take a look at solution. And so there are two components of a solution you need to be aware of. So more about solutions. The two components of a solution you need to be aware of are the solvents. Has anybody ever heard that term solvent before?
Yeah.
Solvent, okay. Dissolves the solute. This is the largest amount in a solution. Water is also known as the universal. As the universal solvent because it dissolves not everything, but many. And so you need to know the definition for solvent. I need to know the definition for solvent. Now, in a solution, you can have multiple solvents. You have one solvent. Solvent is what does the dissolving, and the solute is what dissolves. In tap water, everything that we mentioned fluorine ions, we mentioned calcium ions, we mentioned magnesium ions. All of those ions, would those be considered the solvent or the solute? All of the ions that are in tap water, would those be classified as the solvent or would those be classified as the solute?
Dissolving.
Solute. And H2O is the solvent. Water's doing the dissolving, and all the ions are dissolved into the water. That's the idea that you have to grasp. And so solute, this is always going to be what gets dissolved, and solvent is what does the dissolving. Another way of saying this is what gets. And then the other thing that you're going to want to write down that I'm going to add is there's a technical formula here. Solutes plus solvents, when we put all of that together, we get the solution. you should have the definition for solvent, the definition for solute, and then you should also write the solute. And notice I put the S in parentheses because you could have multiple solutes. Any solutes you have plus the solvent always equals your solution. So that's technically a formula. You can use that formula to add mass or add volume to figure out an amount of solution. We're not really going to do the math of solutions until we do the rest of the math in the class. The math that you'll do some simple math in this lesson, but nothing too much yet. Math is never completely out from the class. But our entire math unit is unit 6. Like it's unit 6. Welcome back. Yes. I'm sorry? Yes. Welcome. All right, so once we've defined, now we've defined what a solvent and a solute is and a solution. The next thing is, well, how do we predict what dissolves in water? And so this is where what we have been learning. How do we know that oil doesn't dissolve in water? We can actually look at the chemical formula and figure that out. How do we know that other things do dissolve in water? And it comes all back to polarity again. And so here we are. Will it dissolve? And so you may want to write as a title, will it dissolve? We use the idea of like dissolves like to tell us what dissolves in water and what doesn't dissolve in water. And so water itself is polar, meaning that water is partially positively charged on one end and partially negatively charged on the other end. Water has partial charges. Water is polar. Because water is polar, water will dissolve anything else that has charges, which leads us to what dissolves in water? Polar compounds. Any polar compound will dissolve at some amount in water. And ionic compounds. Ionic compounds have charges. And so what doesn't dissolve in water? Non-polar compounds, pure elements, do not dissolve. What do I mean by pure element? Think about aluminum foil. That's pure, well, think about aluminum. Aluminum foil is not quite a pure element because there's a layer of salt. Yeah, there is. Yep. But if you have pure aluminum, like the wires that we used copper for our electrodes, that was a pure element. Does that dissolve in water? Pure elements? No. Yeah, we're going to do something when we get to oxidation where we actually have to get the salt off of the aluminum foil before we can react it. Like the top layer we have to get off. And then you can react the rest of the and oxidize it. So what dissolves in water? Polar compounds and ionic compounds. Pretty much anything that has charges like water. And what does not dissolve in water? Non-polar compounds because no charges, and pure elements because once again no charges. So polar compounds because they have charges, and ionic compounds because they also have. And that's what we call it, like dissolves like. So oil can dissolve other non-polar compounds because like dissolves like. And so water is not the only solvent that exists. There are non-polar solvents that exist, but water is the one that is used 99% of the time. That, like in our body, is like 3/4 water almost. Everything, like the cells, are all in a bunch of water. And so that's why we're going to talk about water most of the time. So make sure you're writing down what dissolves in water, polar compounds. Have you put your notes? Give them a little bit more time. Then we're going to go to our next set of questions, which is, will this dissolve in water or not? Can you make that prediction? And so now you can make a theoretical prediction. Will something dissolve in water? You're going to base it off of what we said here. Water has charges and will dissolve anything else that also has charges. So anything polar, anything ionic. Anything non-polar or pure elements will not dissolve in water. So we're going to go ahead and move forward in about 20 seconds. Hi, thank you. Alright, moving forward. So this is the next type of question you could be asked. Will it dissolve in water? First one I've mentioned in passing. Will it dissolve in water? So Al is a pure element, right? Once we have identified that this is a pure element, will not dissolve. Now, there is another thing that could happen. We're not going to discuss it now, but let me bring it up. Just because a pure element will not dissolve in water doesn't mean it won't react with water. Many pure elements actually do chemically react with water to make products. We're not there yet. And a lot of other metals do, just to varying degrees of explosiveness. But all I'm trying to say is the question at hand is not will it react with water, it's will it dissolve in water. Meaning will water be able to surround it, which we're about to talk about. And break it into parts. Different question than will it chemically react. So it won't dissolve. Could slightly react. F2.
No.
You could say it is an element, right? It's a diatomic element, but it is an element. It's also non-polar. If we were to draw it out, you would see that it's this, right? Polar or non-polar. Whether you call it a pure element, which is technically boring, or you call it a non-polar molecule, right? Regardless, it's still not going to be dissolved by water. So it's covalently bonded, right? But it's non-polar. I'm going to go with non-polar, and it will not dissolve. It does not have permanent charges that water can get around. Water will not be attracted to it. And it would actually form. Not because it's covalent, because it's non-polar. H2S is also covalent. It will dissolve. It's non-polar, meaning the electrons are being shared equally. Is the reason. There's no charges. Non-polar means no charges. No charges means it will not dissolve. Okay. So that means draw the Lewis structure for sulfur and 2 hydrogen. This is the Lewis structure. What do we know about this Lewis structure? So it's bent, which means that it's going to be polar, right? Because of the unshared pairs. Oh, if it's polar, will water dissolve it?
Yeah.
Yes. So, yes, will dissolve. The final one is NaOH. What type of compound is that? Na is a metal, OH
Sodium.
are both non-metals. It's ionic, right? That's known as charges. Ionic, you don't have to draw a Lewis structure, you shouldn't. All you have to know is because it has charges that yes, it will dissolve in water.
What is it?
Go ahead, Matt. Go ahead. Alright, so the second type of question that you can be asked, first was what type of mixture of pure substance do we have? Second is, if you're given an element or a compound, will it dissolve in water or not? And why? And so the third component of today's lesson is going to be, well, how much dissolves? If it dissolves in water, how much dissolves? How much is math, right? That's an amount. So you are going to need at least simple calculations today. Hopefully nothing too crazy. Hopefully. Hopefully you don't. Alright, so we've got another set. Will it dissolve in water? Well, there's 5 of them to evaluate.
So all of them.
Will they all dissolve in water? You looked at it for 1.5 seconds. It was up for 1.5 seconds.
Yeah, it's a yes. It's a yes.
Will it dissolve in water for A?
Yes. Yes.
Why?
Because it has a partial.
Not partial, it has a full charge.
It has
Barium
two, the
chloride.
2 charges, it has the barium
Ba
and it
plus 2, Cl minus 1. That has charges, it's ionic, right? Oh, so could I give you the name and ask you if it dissolves or not? Yeah, naming has not left the building. Naming is going to be throughout the rest of the class. So you've got to pick up, this is a metal, this is a non-metal, from the name. EACL, we don't need to write the formula, that's not part of the question. It's just once you determine it's got charges, because it's got a metal and a non-metal, then the answer is yes, because ionic.
Yeah.
Second one, hydrogen monochloride.
Yes. Because chlorine has 3.5 and hydrogen.
yeah.
Electronegativity difference,
It's
polar.
very polar. It's very
So there's a negative N and A, positive N. We're actually going to learn that HCl in water is hydrochloric acid. Not too far from now. By the time we get to reactions, we'll need to know that because acids are dangerous, but we look at them all the time. This is hydrochloric acid, definitely dissolves in water. The answer is yes, because polar is the river. Silicon dioxide.
Yes, because then.
Silicon dioxide.
Oh, no, it's a linear.
Uh-huh.
It's a linear.
When we draw this out, we should come up with this, right? 2 double bonds on each side. So this is linear. So it's like carbon dioxide. It is non-polar, right? So no, because not polar. Silicon dioxide is a major component, actually, which of glass dissolve in water.
Well,
Not the weight, that's hard to know.
what if like
Beforehand it's there. Also does not dissolve in water.
Nah, you're gonna melt it.
Not dissolving. Ammonia, which I had to give you the chemical formula because you have not been asked to memorize that name to formula. So the chemical formula for ammonia, which is a household cleaner, by the way, is NH3. is that going to dissolve in water? The fact that I mentioned the household cleaner already kind of gives it away. If you've ever seen ammonia before, it 95% of water, 5% of it is actually ammonia. And so it is something that's definitely dissolved in water. Why though? Like looking at its chemical formula. What tells us?
Oh, it's very cold.
Polar, got that unshared pair of electrons, got that big difference in electronegativity between nitrogen and hydrogen, and so this will definitely, so polar, so the answer is yes, because polar. Once again, what we learned last unit in polarity is in this unit a lot. So you've got to be able to know if something's polar or not polar, or else you're not going to be able to make a lot of the decisions you need to make in this. Ammonium hydroxide. Ammonium, what was that? Ring a bell? Even if you don't remember exactly what it is, you remember what these things are?
Yes.
What are they? Called ammonium hydroxide. There were other ones like nitrate and carbonate. What are they called? Even if you can't remember the formula, what are they called? Together, they're called polyatomic ions, aren't they? And if you know they're called polyatomic ions, it means they have charges, and if they have charges, will they dissolve in water? Yes. Yes, right? NH4 plus 1. Hydroxide is OH minus 1. We got those charges there, and the answer is it's ionic, right? So yes, because ionic, because there's ions there. Yes. Yes, no. So they're not all yes. 4 out of 5 were yes, actually. So that's a pretty good guess. But almost all of them would dissolve in water.
Take a picture.
All right, so that was going over will it dissolve in water. So the next question is, assuming that it does dissolve in water, something dissolves in water, is there a limit to how much it dissolves? Or can water just infinitely dissolve the solutes?
No, part of
So you
it.
can put like a billion grams
It
of
can infinitely dissolve water.
it just
I mean, it can dissolve water.
into itself, like just combine.
We might not be able to see it, but a part of it's still there.
So before we do the math, let's talk a little bit about the solution formation process, like what is actually happening to these polar compounds and to these ionic compounds at a molecular level. And so I'm going to pause here for 20 more seconds. Anybody else need a picture or is writing down? Please make sure to do so now, and then we're going to continue. Good. Okay, so here we go. This is the solution formation process. And you should write down at minimum this, and that looks like a lot. But you should have the diagram in your notes somewhere. Because this is the idea of what goes on. In the process of a solution, and this is an example of salt. Salt, when it enters water, starts with ion-ion bonding. And these ion-ion forces are broken apart in water. Now, you might have to help it. How would you help salt dissolve better in water? Heat it to provide more kinetic energy. What else could you do? Right. So if I've got a little bit of salt and I just throw it in water, it might just fall to the bottom, right? But then your concentration won't be homogeneous throughout. And so what we do is we help it along, and all we gotta do is stir it for unspecified amount of time until everything dissolves, which we practiced in our last lab, if you'll recall. And some things dissolved really quickly, and some things like copper sulfate took 3 or more minutes. I don't know if you remember that from a couple weeks ago. The copper sulfate? So then, skill issue for someone? Like myself? then what we're actually doing at the molecular level is we're applying force to break up these ion-ion forces, and new bonds are forming between water and the ions. These new bonds that are forming, notice there's many of them. So it ends up becoming a strong force, strong enough to be favorable in comparison to the ion-ion connection. We call these bonds, because it's an ion with water, what do we call those intermolecular forces? It's one we hadn't really done in that lesson, but it was mentioned in the Ed Puzzle video. It's called ion dipole forces. So the force of water surrounding your ions, and why water is now attracted to those ions, it's called ion dipole. Now, once you've made your homogeneous solution of salt, will you actually see the salt anymore? Or will it look like it's disappeared for the most part?
Perfectly mixed, no?
If it's perfectly mixed, you won't really see the salt. Now, if you were to taste it, you'd be like, oh,
You see
super
red line.
salty. But you won't really see the salt there anymore. All you see is the water. Does it make sense that if the Na plus and Cl minus are separating and all you have is a bunch of water around your Na plus and you have a bunch of water around your Cl minus as well, you see all the water, but you don't see the ion. The water has crowded it out. As long as you have enough water to do so, it will dissolve your ions. And so I'm giving you some time to write this out. You should have an example of the diagram. Back. So it looks like, can't even see the salt anymore. All I see is the water. So this is the actual process of forming a solution. The ion-ion, or whatever forces you have, are separated from each other, and then water makes new bonds. This is called solvation. Yes. So I'm giving you some time. Make sure you get down the diagram and what solvation is, and then we'll continue. So all the salt I put in, it did dissolve. But could I just keep dumping salt in and it forever dissolve?
No.
Where would the limit be reached? When you run out of water to surround it, right? When you don't have enough water molecules to make all of these ion dipole forces anymore, because you have too many Na plus ions and too many Cl minus ions, you're not going to be able to dissolve anymore. Well, we're not going to be able to really look at this at an atomic level. So we look at it numerically. And experiments have been run on how much can dissolve. And it's well studied how much can dissolve at various temperatures. And I printed out that graph for you. It's on today's handout, the bottom of today's handout. And we call that solubility. How much will dissolve? I'm giving a little bit more time and then we'll move into that. And so the last part of today's lesson is to look at the math. You may want a calculator because the calculations do not require scientific notation. You can use any simple calculator for this process. You can use the Desmos online. You can use your phone, although you won't be allowed to use your phone for a test. You can use it for just the practice question. So we're about to get to that. You can. The part that you have to write is here, solvation. This is just talking about the process of what happens. So what's actually happening when I put salt in water is the Na plus and Cl minus ion forces are separating, and then new bonds are being formed between the water and the positive ion and water and the negative ion, which is why you need a positive ion or a negative ion in order for it to dissolve in water. No charges, no dissolve. Water won't be able to surround it. That's the idea. So I think last year I reorganized a little bit. We already talked about hydrogen bonding earlier, so I'm not going to have you write this down again because we already talked about hydrogen bonding and that it gives water many of its is because of water's ability to hydrogen, that it can dissolve so many things because it's so polar. It's small too, small and polar. So if you get around a lot. All right, I'm gonna go ahead and move forward now. So our final question of the day, and you've got this slide printed. The reason why you've got this slide printed is because you are going to need to look at this graph to make decisions. And so I've got a ruler for you. I didn't have them put out last class, but I did put out rulers this class so that you can use a ruler whenever need be. Whenever you're looking at a graph, and for all Cambridge science exams, I would like to say, at some point you may need a ruler for a graph. So they allow a ruler and a scientific calculator on all Cambridge exams. And most of the time, we'll put them out in advance, just in case, because we don't get to look at the exams in advance, but just because we know that there's graphs that could be there, we'll usually provide a ruler. That's for the marine science, the environmental, the chemistry exam, the bio exam, any of them. Because we do have to do some interpretations of graphs. And so we're just doing some light work with graphing here. Our question is, how much will dissolve? And so what you see here is something called the solubility curve. That's what this graph is. The amount that a substance dissolves in water, we refer to that as the substance solubility. So solubility is just how much dissolves in water. And there's technically a formula for it. It's X grams of solute for every 100 grams of water. This is what we call the solubility. X grams of solute for 100 grams of water. So you can look at this graph, and for the homework you're going to get today, and for the quizzes that you'll have at the beginning of next class, and the unit test, you would also be given the same graph. This is not every not even close to every compound that exists. This is just a variety of famous compounds and how much they dissolve in water. And so if you look at it, you can see the variation in temperature and see how that affects the solubility of many different substances. What is the average trend? You think when the temperature goes up that for most things, the solubility goes up or the solubility goes down? For most, there are exceptions. Cerium sulfate. Cerium. That's like, gotta be the F block. Doing something strange over there in the F block. And NaCl stays almost exactly the same no matter what temperature. Like a slight, maybe a slight bit down. But for most ionic compounds, you'll notice that it either slightly increases or it greatly increases. And then sugar is wild. I remember when I was first teaching high school chemistry, we tried dissolving sugar in water, and we just kept adding. Look at that. For 100 grams of water at a room temperature, you need more than 200 grams of sugar. That means double the amount of sugar than water. That's wild. Why do you think, before I even go on, is there a reason why sugar dissolves so well in water on a molecular level?
Because it's
Let's take a look at sugar real quick, right? Sucrose. Let's take a look at the structure of sucrose. That's what it is. The C11H22O11. It's this. Which you have likely seen in your biology class.
Wow. Wow, I didn't know sugar came in that whole room.
That is sugar, right? What you notice going on here?
There's a lot of HOs.
There's a lot of HOs or OHs.
Where's O's?
What about that? What is that in your molecular force? Hydrogen bonding, 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 hydrogen bonding. It's got a whole lot of hydrogen bonding going on. So it is very easy for water to surround sugar, which is why so much of it dissolves in water. It's because of its great ability, because it's super polar, super polar. And so there is an explanation to why sugar is so soluble. And so what you're going to have to look at here is just graph. And you're going to look at different temperatures and see what the solubility is, and then you're going to make comparisons. And so, for example, if I ask you, how much KBr dissolves at 50 degrees Celsius, what would you do? How much KBr dissolves at 50 degrees Celsius? Look at your graph and see if you can figure it out. Yes. how much KBR dissolves at 50 degrees Celsius. Go to your graph, go to the temperature of 50, go to KCL, and then you've got a ruler, so you can just go straight across. And what is that? And you can estimate. Like, it's a little bit, my drawing's terrible. Probably like 35. Something like that. Actually, no, I think it actually is close.
This is roughly to 40.
Approximately 40 grams. And so 40 grams what? 40 grams of KCl in 100 grams of at 50 degrees Celsius. So you gotta establish the temperature, and then you know how much dissolves in 100 grams of water. Now you may be asked how much dissolves in a different amount of grams of water. Could you figure that out? It's proportional, so you will be able to figure out. And we'll take a look at some questions like that shortly.
I got 54.
50.4.
0.
Oh, I see. That would be 0.4 grams for every 1 gram of water. Yes.
I was gonna ask, how much can dissolve below 0?
Right. Water is ice, so whatever you have will just be stuck in the ice. The ice melts. Good. Good point. So let's take a look at the types of questions. And you should just write the question. You don't have to write the graph down because you've got it in front of you. So just write the practice questions down themselves, and then we'll solve them. First practice question. Using the solubility curve shown. So write this down. So you have it in your notes. This is the type of question you can be asked. What is the maximum amount of grams of KBR that will dissolve in 300 grams of water at 40 degrees Celsius? What would you do for that? You've got your graph. Write the question down. I'm pausing to give you time to write the question down. This is the type of question you're going to be asked, and there's a lot of questions in the homework today with the graph. You're definitely going to want to know this process. This is the last homework, the one I'm giving today before winter break. I will not be giving you a homework on just the last.
I got 0. What? And you just keep going.
Huh?
3.
What?
0.1.
No way. No way. I want to know how many grams will dissolve in 300 grams of water. I know what you're doing. I think you're finding the amount that dissolves in 1 gram of water. I think.
What did it like?
That's not.
You multiply it.
Well, it depends on what you're doing. If you divided it by 100, then
By 300?
or multiply by 3 if you just look at the number they are. It sounds right.
120.
Let's take a look at KBR at 40 degrees
Yeah,
Celsius.
let's solve this first. Like,
It's approximately, we can
It's a
approximate.
little bit less than
It's a little bit, it's probably 75,
like a 50.
right? It's a little bit less. Let's approximate that at 75. If you approximated it at 80 on the test, I would not. But it's a little bit under 80. It's 75 on the test. And so what this says is that reading the graph, I know that 75 grams of KBR dissolves in 100 grams of H2O at 40 degrees Celsius at this specific temperature. That's the solubility. Now, is 75 my final answer?
No.
No. So here's where you have to understand proportionality. You don't have 100 grams of water. You have 300 grams of water. The numbers are easy, so it probably makes sense, hopefully, to you, that you would multiply by 3.
3. Yeah. No,
Because
okay,
in
but
order to
2.25.
get this to be 300 grams of water, you're right, 3 over 3. So to get this to be 300 grams of water, you have to multiply both the top and the bottom by 3.
Yeah.
And so you would get 300 grams of water is 75 times 3, which is 225 off the top of my head. Okay.
Yeah, I got 2.25.
And so 225 would be the answer. That's because you're dividing. But not multiplying.
No, I multiplied 100 by 3.
You could also do this. You could do 75
Oh.
grams KBR over 100 grams H2O equals 300 grams H2O over X. This is the other method. If the numbers aren't so easy,
Can you tell me that 2.25?
2.25 is not right, but I know how you got it. You did 75 divided by 100, and you got 0.75, which is the amount of grams of KBR per 1 gram of H2O. But because you've made it for 1 gram of H2O, you now need to multiply by 300 because
I
you
just
have to.
multiplied that 75 over 100 by 50.
Right, but it has to be
That was a correct ratio.
right. You have to multiply this by 300 because these both have to go to 300.
Yeah.
If you multiply 1 by 300, you have to multiply 0.75 times 300. It's 0.75 times 300. Anyway, this is the one method what I showed here. The other method, if the numbers aren't so simple and you can't just figure out that it's multiplied by 3, right? Because we were able to look at that and be like, okay, 300 is 3 times 100. Those numbers are easy. If they're not easy, because they're not always easy, then you would set up a proportion. And so I put here a proportion. It's the same idea. 75 grams of KBR for 100 grams of water equals X would be the new amount of KBR, right? In 300 grams of water. And then you would have to solve the proportion, which means you would cross, multiply, and solve for X. This will always work, so you may want to write it down. If the numbers aren't easy, then the best way to do it is to set up a proportion. Because this tells you the variation. Once I increase my water, I will know that I have to increase my KBR. But if I don't know by what, then you set up a proportion. All right, so that was practice question 1. There's one more set of definitions we have to go over before we do the other practice question. These definitions may be familiar to you. You'll let me know if you've heard of them before. Unsaturated solution, saturated solution, supersaturated solution. Those are the final 3 definitions that we're going to go over. Yeah. So what I have in front of me, what I created here is called an unsaturated solution. Why would I call it unsaturated? The salt that I dissolved in water is an unsaturated solution. No, I didn't, but there's salt in there. There's definitely salt in there. Why is it called unsaturated? So if you don't know, we have one more set of definitions to go over. What is an unsaturated, a saturated, and then a supersaturated solution. All right, I'm moving forward now. These are the definitions you need to know. So an unsaturated solution, why I would classify the solution I made with salt and water is an unsaturated. And the solutions you're going to make on Wednesday are unsaturated solutions. An unsaturated solution is one where I could still dissolve more solutes. Like I dissolved some solute, but I could still add more and it will still dissolve. I have not reached my saturation point. Whereas once you have saturated the solution, this means anything else you add, you cannot dissolve anymore. You have dissolved as much as you possibly can, and anything else will just fall to the bottom. No matter how hard you stir, it ain't dissolving because you don't have enough water to dissolve it anymore. You ran out. So you're going to want to know the difference between those 2 definitions. Unsaturated means I can dissolve more. Saturated means I cannot dissolve more. It has dissolved as much as it possibly can. And because we're talking about the math, we're going to have to work out some questions with saturated versus saturated solution.
What's a supersaturated?
I'll explain it. It is a very specific process that has to do with variation. The main two you're going to see regularly are unsaturated solution and saturated. And you should have heard the word saturated in another context. For example, if it rains a lot here, we say the ground is saturated with very wet. It will flood. If we have any more rain, it will flood. I'm pretty sure our ground is that right now after last week. So basically, saturated means cannot really hold any more, whereas unsaturated means you could hold more. And so that meaning is still the same here. Unsaturated, you could dissolve more. Saturated, you dissolve as much as you can, nothing else. So the two definitions, and then we'll take a look at a couple of math questions. With these definitions, then we'll define supersaturated, which is a very, very specific process. For the math questions, once again, you need the graph for this lesson. You need that graph, and you need that little formula, which is X grams of solute for 100 grams of water. Here we go. Let me pause for 20 more seconds for those of you who are writing. Remember, just the definition for unsaturated and saturated here. Good? Ready? Here we go. So, practice questions, there's a couple of them. If 20 grams, you should write them down so you have them to look back at. Because, like I said, your homework's going to be a lot of questions like this. And by a lot, I mean
1,000.
there's like, I'd say 25 questions here easily. But this is the last homework before winter break. That's the good news. Like I said, I'm not giving you homework on Wednesday, just the lab. We're going to take a look at the first question. There's two questions here. First one is, if I had 20 grams of NaCl and 100 grams of water at 50 degrees Celsius, would we call this a saturated or unsaturated solution? Which one do we have? What do you think we should do first? Let's think about what is our thought process here. What should we do first? Should always find how much salt. Okay. We're going to find that from the graph. We got to find how much dissolves NaCl in 100 grams of water at 50 degrees Celsius. So it's about a little bit less than 40, right? 35-ish? A little bit less than 40. 30. Okay. Now compare. Is the number you have more or less than the solubility? 2. Is your amount, is the amount to be dissolved more or less than the solubility? Is it more or less? 20 grams, it could dissolve 35. You have added 20 grams. Is 20 more or less than 35? Less. So if it's less, would that mean it's saturated or unsaturated? By definition. Saturated means you can't dissolve. So at 20 it's done. So what would it be? Unsaturated. So unsaturated means before solubility, means less than the solubility. And saturated means equal to or so I'm writing this down to help you out as you're working through your question. Unsaturated means you have less than the solubility. Saturated means you have equal to or more than the solubility in the solution, but you have leftover on the bottom. Like it hasn't all dissolved. Once you've reached the saturation, you do have leftover on the bottom. So we're going to take a look at the second question. I'm just giving you a little bit of time. We're close to done. It's just a couple practice questions and go over supersaturation. Remember, you've got the graph in your notes. I gave it to you on a handout. And it's also going to be on your handout for your homework. 60 grams of KCl and 100 grams of water. Just placed in 100 grams of water with no other information given to you. 60 grams of KCl. So the first step, find how much is supposed to dissolve, right? Use a ruler, find how much grams is supposed to dissolve. That's going to be, you're right, that will be around 40, I would say.
So it's less than the 60.
Right. Well, one, the solubility is 40 grams in 100 grams of water, right?
Yeah.
So the second question is the amount you've been given to dissolve more or less than 40? More. So this means that your solution must be saturated. Could I also ask you how much is left at the bottom? We're good. How much is left at the bottom? That I couldn't dissolve. Should be 60 minus 40, which is 20 grams. So if you're doing the mental process, you have to do to get that. Again, the numbers are simple. All right, we've got one more definition to look at. Let me double check. I'm pretty sure. There are a few questions about supersaturated in here, so you do have to go over that definition. Now, supersaturation sounds interesting. Supersaturation. It is a specific process, and it's actually a little bit difficult to do, not impossible, but it's a little bit difficult to do. What supersaturated solution is when you take something that the solubility changes with an increase in temperature, and you dissolve as much as you can at high temperature, and then you let the solution cool down. It turns out that if you leave the solution undisturbed, when you cool it down, you'll still have the same amount that was dissolved at the higher temperature dissolve at the lower temperature. So you're theoretically dissolving more than what is suggested by the solubility. And so a supersaturated solution, and you should write this down, it is a unique situation in which a solution will hold more solutes than is theoretically possible. So more than the maximum given by the solubility chart at a given temperature. And like I said, this can only happen. You don't have to write this down, this is just me explaining the way that it happens. This can only happen if you raise the temperature of the mixture to increase the solubility, and then you let it sit. Don't touch it. If you even just like touch the mixture, everything comes out all at once. It's really cool. Everything crystallizes all at once.
Was there some of the cups back there?
Yeah, some that were stuck to the bottom. Some of your mixtures got stuck to the bottom. They just like it's like sludge. It's like sludge at the bottom. Some of that sludge is like toxic sludge. That's so much food coloring. I'm not splatting that on my next sweater. there, yeah?
Yeah, try to get.
Right when we're done. Yeah, this is the last slide for the day. After you write down this definition, I'm passing out the homework. There are a bunch of questions, so you may consider wanting to get started with it. Like I said, this is the last homework of the regular year of 2023 for this class. So make sure you finish it, you turn it in at the beginning of class on Wednesday. The first page is just the chart, and then on the back of the first page is the actual question. So go ahead and get started on those. If you want to get to the coloring on your shirt, you can do that.
Well, 100% yes.
I'll show you where it is after I finish that.
I don't know. We don't.
No, I have, no.
Oh, you moved them. Okay.
I was trying to get it out, but I didn't want to splash it.
I don't think you're gonna get this
Oh,
out.
yeah, no, I see mine.
It made like
Yeah.
a crystal walls around itself.
Grab the puff. It's
Yeah,
available
pour
yet.
it out and try to like,
In the sink in the back.
okay,
Hold on. Wait, let that come off.
You're just gonna. You know. You
I mean,
just
there's-
got your hand.
Nitrile gloves, the regular gloves, they're in the regular spot.
Wait. Wait.
Alright, so you've got a little bit less than 10 minutes left in class. Go ahead and get started. On the homework. Here you go. Yeah, yours is here. I was trying to get it out because I thought it was cute. But you can pour it out of the yours is up there.
Oh, it's evaporated? That's what happened, or like?
Actually, the evaporation rate in here is pretty high, so then you have to wait for whoever does to come back. I believe it's me.
Mine got it.
Then if you want, if it comes out, you can let it dry on a paper towel.
So yours did come out.
There you go. This one today. Try. I don't think it's but it's gonna mess up the shape.
Well,
It's most things when they come out of the cocoon, they become better.
Like butterflies?
like a butterfly, exactly.
Oh my goodness.
Mine was a Christmas color green, but it was in powder form.
You said an unholy green.